Apparently, I forgot a few things relating to photons and electrons in the previous video, so writing for this video is genuinely difficult for me because how do I even start diving into a part that was supposed to be mentioned in the previous one? There's no smooth transition for this, so let's just start with the de Broglie theory. In 1924, Louis de Broglie proposed his PhD thesis, in which includes a groundbreaking theory of matter. According to this theory, all matter can behave as both a particle and a wave, though if something behaves more like a wave, then it behaves less like a particle, and vice versa. To determine whether something acts more of a wave or more of a particle, the wavelength calculated from the equation is compared to the overall system to see whether if it's bigger, smaller, or equal to 100. If the value is bigger, then it's more of a particle, and if it's smaller or equal, then it's more like a wave. To establish the equation relating to this, we must bring up the famous formula that when sprinkled into anything makes it look vaguely scientific, E equals mc squared. Once again, we will link the photon's energy equation with this, and we get hc divided by lambda equals mc squared. Cross out c from both sides of the equation, and we get h divided by lambda equals mc. H is 6.626 times 10 by the power of negative 34 millisecond. C is velocity. Lambda is the wavelength in meters, and m is weight in kilograms. This equation is colloquially called the de Broglie wavelength. To visualize how something can be both a wave and a particle at the same time, let's imagine an object, for example, a ball. This ball is a particle, of course, because you can touch it along with the particles that makes up the ball. So that's the particle side. Onto the wave side, the photons emitted from the ball hits your eyes along with its electromagnetic waves. But according to the equation above and some rough estimates, we can be sure that the wavelength is nowhere close to 100 in comparison. So the ball exists more of a particle and less of waves. This was supposed to be tagged along with quantum numbers, but if I don't stuff it here, the video is going to be about like 3 minutes long, and that to me won't be enough to qualify as an education video. Imagine this. A person is driving a bit fast after some fun time at the pub. On the road, there is a single mother and her young kids crossing. With their remaining consciousness inside, the person hits the brakes, causing the car to spiral out of control. The car, however, will eventually stop since gravity is pulling the car down. But what about an electron, something that is smaller than even protons and neutrons, of which the sole reason it's still remaining in orbit of an atom is from the attractive force of the proton? Gravity couldn't pull that car down now, could it? This electron car would be all over the place, and the certainty of its positioning can never be determined. And that's basically the Heisenberg principle, which is that you can never determine the exact position of something that is as molecular as an electron. Anyways, onto the formulas. Delta x multiplied by delta px is larger or equal than h divided by 4p equals h cross divided by 2. H cross here equals h divided by 2 pi, and we can call h cross the shortened Planck's constant. Delta x is the uncertainty in position. But what does that mean? If we predict the electron to be at point A, but the slippery little electron is actually at B, delta x is the distance between A and B. The lower the delta x is, the more accurate the predicted position of the electron. The next one in this hodgepodge is delta px. We call it uncertainty in momentum. Delta px equals m multiplied by delta vx, and delta vx is the uncertainty in velocity. Just like delta x we established above, the uncertainty of both of those is the difference between the predicted values and the actual value. Once again in this equation, the multiplied values of delta x and delta px is higher or equals h divided by 4 pi, which if you calculate, you get an abysmally small number. And just using the error numbers calculated from normal values like centimeters or meters, it is still flabbergastingly larger than the h divided by 4 pi. Let's just take some measuring instrument as an example, like a ruler. You can't see it, but there exist value errors in the lines. Take it to the molecular level, and there's uncertainties in positions of electrons in the orbitals as the Heisenberg's principle established, and so it makes the molecular bonding of the atom that makes up the ruler shaky. So basically, everything is all molecularly uncertain. Let's consolidate all these theories by having some exercises. Pause if you want to do it by yourself. If not, here's the solution. For this one, we have to change the units. As we have established, SI units are the way to go for exercises like these. So 2.5 grams equals 2.5 times 10 by the power of negative 3 kilograms. 36 kilometers per hour is 10 miles per second. Plug this in the formula, h divided by lambda equals mc, and we get 6.626 times 10 by the power of negative 34 divided by lambda equals 2.5 times 10 by the power of negative 3 times 10. So the answer is 2.65 times 10 by the power of negative 32 meters. B is easier than A since the units are already in SI. So we change C, or the speed of light, with 3 times 10 by the power of 8 and apply it with the same formula in A, and we get the wavelength value of 4.85 times 10 by the power of negative 9. C is just an altered version of A and B. First, we turn 15 grams into 0.015 kilograms. Then, we will solve for V using the same equation. After solving, we get V equals 88.35 miles per second. To calculate delta X, or the uncertainty in distance, we multiply the error percentage with the given distance. So 1% multiplied by 0.5 times 10 by the power of negative 9, we get 0.5 times 10 by the power of negative 11 meters. We have the formula delta X multiplied by delta Px is larger or equal than h divided by 4 pi. So Px equals delta Vx multiplied by m is larger or equal than h divided by 4 times pi times Vx. Move the m onto the other side of the equation and we get delta Vx is larger or equal h divided by 4 times Px times m times x. Solve this and we get Vx is larger or equal 1.16 times 10 by the power of 7 miles per second. Comparing this to the supposed electron's velocity, and we see that this is at least 3 times higher. This proves that you do not know how much the electron will accelerate or decelerate. Alright, this is the end of this quote-unquote intermission video. I'll see you next time where I'll actually show you quantum numbers and wave functions as a bonus.